Right now, something is pulling you. You cannot feel it, but your galaxy is racing through the void at 2 million kilometers per hour toward a gravitational anomaly we barely understand. The universe you think you know might be a temporary illusion, a bubble waiting to collapse at the speed of light. And there is a non-zero chance that everything you remember never actually happened. This is not science fiction. These are not fringe theories dreamed up by conspiracy theorists in basement forums. These are ideas that emerge from peer-reviewed papers, from observations made by the world's most powerful telescopes, from equations written by Nobel laureates. These are theories that keep cosmologists awake at night, puzzles that refuse easy answers, and questions that grow more disturbing the deeper we look. Picture this. At some point in the next 100 seconds, you will learn about a field permeating all of space that could, without warning, quantum tunnel to a lower energy state and obliterate the universe at light speed. You will discover that massive black holes are wandering through the galaxy right now, invisible, hungry, drifting through the darkness. You will confront the mathematical possibility that you are not a biological organism, but a spontaneous fluctuation of particles in the void, complete with false memories of a life you never lived. And every one of these scenarios is permitted by the laws of physics as we currently understand them. Over the next 2 hours, you will discover 10 ideas that challenge everything we assume about reality itself. They are not comfortable, they are not reassuring, but they are honest. Windows into a cosmos that is stranger, more fragile, and more terrifying than the one we were taught about in school. Some of these theories have been tested in laboratories. Others await future observations. All of them force us to ask, what if the universe we think we understand is just the surface, and underneath lies something far more unsettling? If you are looking for cosmic horror, you will not find it in fiction. You will find it in the equations, in the data, in the careful observations of astronomers who looked at the universe and realized that something was very, very wrong. Prepare yourself. We begin. Theory 1. The universe is a false vacuum waiting to destroy itself. Picture a marble sitting in a shallow valley on the side of a mountain. It looks stable. It rests there, motionless, seemingly secure. But it is not in the lowest possible position. One small nudge, a vibration, a gust of wind, and it could roll down into a deeper valley below. The marble, comfortable in its temporary home, has no idea it is perched on the edge of oblivion. This is our universe. According to quantum field theory, empty space is not truly empty. It is filled with invisible fields, and one of them, the Higgs field, gives particles their mass. When physicists discovered the Higgs boson at the Large Hadron Collider in 2012, they measured its mass with extraordinary precision. The number they found was troubling. At approximately 125 billion electron volts, combined with the mass of the top quark at roughly 173 billion electron volts, the measurements suggest something unsettling. We may not be living in the true vacuum. We may be living in what physicists call a false vacuum, a metastable state that could at any moment collapse into a lower energy configuration. Think of it this way. You are standing in a house built on a frozen lake. The ice is thick, and you feel secure, but underneath that ice is liquid water, a lower energy state. The ice is only temporarily solid because the temperature is cold enough to maintain it. But if the temperature rises even slightly, or if someone creates a crack in the ice, the entire surface could collapse. One moment you are standing on solid ground, the next you are plunging into the freezing depths. The false vacuum is that ice, and we are all standing on it. The false vacuum is not science fiction. In 2024, researchers using a quantum annular with 5,564 superconducting qubits observed vacuum decay dynamics in real time. They watched as bubbles formed in a metastable state, miniature versions of the catastrophic process that could one day consume our universe. The experiment, published in Nature Physics, confirmed that the mechanism is more than theoretical metaphor. It can happen. It has happened in the lab. And if it happened to our cosmos, we would have no warning. Let that sink in. Scientists have created false vacuum decay in a controlled experiment. They have watched the process unfold, measured it, studied it. The physics is real. The only question is whether our universe is truly in a false vacuum state. Here is how it would unfold. Somewhere in the vast expanse of space, maybe in a distant galaxy, maybe in the void between superclusters, maybe right here in our own cosmic neighborhood, a tiny region of the universe would quantum tunnel from our false vacuum into the true vacuum. Physicists call this process bubble nucleation. In the 1970s, Sidney Coleman described how it would work. A field trapped in a shallow valley of energy would, through quantum tunneling, drop into a deeper one. The transition would not happen all at once. It would start as a bubble, a sphere of true vacuum perhaps smaller than an atom. But once formed, that bubble would expand at the speed of light. No slowing down, no warning signs, no gradual transition. Light speed is the ultimate cosmic speed limit, and this bubble of destruction would race outward at exactly that limit, rewriting the laws of physics as it went. The wall of this expanding bubble would be a boundary between two universes with different physical laws. As it swept outward, it would rewrite the fundamental constants of nature. The strength of the electromagnetic force, the masses of particles, the behavior of atoms, all of it would change. Electrons might no longer orbit nuclei in stable patterns. Quarks might not bind into protons and neutrons. Chemistry as we know it would cease to exist. In the new vacuum, there would be new rules, new constants, new physics, and nothing from the old universe could survive the transition. Imagine the laws of physics as the operating system running on reality. Vacuum decay would be like a forced update that deletes everything and installs a completely incompatible system. All your files, every star, every planet, every atom would be erased, and the new system would not run the same programs. Life, as chemistry, as biology, would be impossible. You would not see it coming. Because the bubble expands at light speed, the information about its approach would arrive at exactly the same instant as the bubble itself. One moment you would be reading these words, your neurons firing in complex patterns that give rise to thought. The next moment, the fundamental structure of matter would dissolve. No pain, no warning, no final thoughts. Just annihilation, rewriting reality atom by atom, faster than any signal could travel. Think about that. The speed of light is supposed to be the ultimate speed limit, the cosmic speed of information. But in this case, it becomes the speed of extinction. The bubble carries its own destruction, and by the time light from the bubble's edge reaches your eyes, the bubble itself has already reached you. There is no running. There is no hiding. There is only the instant transition from existence to non-existence. How long do we have? The calculations vary, and this is where things get both technical and terrifying. Some physicists estimate that the decay time for our current vacuum state could be longer than 10 to the power of 100 years, a 1 followed by 100 zeros. To put that in perspective, the current age of the universe is only about 10 to the power of 10 years, a 1 followed by 10 zeros. We are talking about timescales so vast they dwarf the entire history of the cosmos by 90 orders of magnitude. On these timescales, the decay is effectively impossible. But the key word is could. The calculation depends on physics we do not yet fully understand. If the Higgs field is coupled to gravity in certain ways, or if there are additional fields we have not discovered, the timeline could be shorter, much shorter. Some models suggest that high-energy cosmic rays, quantum fluctuations in the early universe, or interactions with exotic particles could trigger the decay much sooner than the baseline calculation suggests. And here is the truly unsettling part. The universe might already be decaying somewhere far beyond our cosmic horizon. Our observable universe is limited by the speed of light. We can only see about 93 billion light-years in every direction. The distance light has had time to travel since the Big Bang, accounting for the expansion of space. But the universe could be vastly larger than what we can observe. It could be infinite. And if it is infinite, then somewhere out there, a vacuum decay bubble could have nucleated billions of years ago and is now racing toward us across the void. We would never know until it arrived. Stephen Hawking once remarked that the Higgs potential has a worrisome feature. It might allow the vacuum to decay catastrophically. In 2014, he noted that at incredibly high energies far beyond anything we can create in particle accelerators, the universe could become unstable. The energy required is roughly 10 to the power of 15 billion electron volts, about 1,000,000 times higher than what the Large Hadron Collider can produce. But such energies existed in the early universe, during the Big Bang. If the vacuum can decay, why did it not happen then? One possibility is that we got lucky. Cosmic inflation, the rapid expansion that occurred in the first fraction of a second after the Big Bang, may have smoothed out any high-energy fluctuations that could have triggered decay. The inflationary period stretched space so quickly that any dangerous quantum bubbles were diluted away, leaving us in a smooth, low-energy state that has persisted ever since. Another possibility is that unknown physics stabilizes the vacuum in ways we have not yet discovered. Perhaps there are additional fields, extra dimensions, or quantum corrections that prevent the collapse. String theory, for instance, predicts a vast landscape of possible vacuum states, and our universe might be sitting in one that is more stable than the simple calculations suggest. Or perhaps the clock is still ticking. Perhaps we are living in the brief window between the Big Bang and the inevitable decay. Perhaps in the grand scheme of cosmic time, our universe is just a temporary fluctuation, and the true vacuum will eventually claim everything. Dr. Tommy Markkanen, a cosmologist who has spent most of his career studying Higgs vacuum metastability, offers some reassurance. In a 2020 interview, he stated that according to the standard model of particle physics, the probability of vacuum decay is mind-bogglingly small, so small that in every practical sense there is no chance of it happening. The decay probability, he explained, should be less than once every 13,800,000,000 years, simply because the universe has successfully survived at least that long. If vacuum decay were likely, it would have already occurred. But here's the unsettling part. The standard model may not be complete. Physics is full of models that work beautifully within certain limits, but break down when pushed further. Newton's laws of motion work perfectly for everyday speeds, but they fail when objects approach the speed of light. That is when Einstein's relativity takes over. Similarly, the standard model of particle physics has been extraordinarily successful, predicting the existence of particles like the Higgs boson with stunning accuracy. But physicists know it is incomplete. It does not include gravity. It does not explain dark matter or dark energy. It does not account for the matter-antimatter asymmetry of the universe. If future experiments reveal new physics beyond the standard model, the vacuum stability calculation changes. If we discover that the top quark mass is slightly higher than current estimates, or if we find new particles or forces, the false vacuum could become more unstable. Vacuum decay might not be impossible after all. It could be improbable but inevitable given enough time. And if the universe lasts forever, as many cosmologists now believe it will, then even an event with infinitesimal probability becomes certain, eventually. So what does that mean for us? It means we are living on borrowed time, in a universe that is stable for now but may not remain so. The marble sits in its valley, unaware of the deeper valley below. We build our civilizations, explore our cosmos, and ask our questions, all while perched on a knife edge of quantum mechanics. The laws of physics that allow stars to shine and life to flourish may be temporary features of a temporary vacuum. One day they could change, and when they do, everything ends. But wait, there is another layer to this nightmare. If the universe can exist in multiple vacuum states, then every possible configuration of physical laws might exist somewhere in some bubble of space-time. Our universe, with its particular values for particle masses and force strengths, may be just one bubble in an infinite foam of universes, each with its own physics. Some of those bubbles would be stable, true vacuums where the laws of physics are permanent, others would be false vacuums waiting to decay. And if bubbles can nucleate spontaneously from the quantum foam, then the multiverse is constantly giving birth to new universes, each with random physical laws. We would be living in a cosmic lottery, and the prize for losing is complete annihilation at the speed of light. Now zoom out. Imagine you are looking at the universe from outside, from some higher dimensional vantage point. You see countless bubbles of space-time, each one a universe with its own laws. Some are stable, some are decaying right now, collapsing into lower energy states and rewriting their physics. And our bubble, our universe, sits among them, temporary, fragile, balanced on the edge of stability. One nudge, one quantum fluctuation, one high-energy cosmic ray striking the Higgs field at just the wrong angle, and it all ends. This is not meant to frighten you into despair. It is meant to show you what the equations are telling us. This is where physics leads when we follow it honestly. The universe is not a safe, permanent structure. It is a dynamic, evolving system governed by quantum mechanics and general relativity. And those theories, beautiful and powerful as they are, permit outcomes we would rather not think about. But they also permit this, a universe stable enough to last 13,800,000,000 years so far. A universe where stars can form, planets can cool, and life can emerge. A universe where conscious beings can look up at the night sky and ask, what if there is more? And that, in its own way, is astonishing. The false vacuum teaches us humility. It reminds us that the universe does not owe us stability. We are here because the conditions happen to be right, for now. And if those conditions change, we will not be here anymore. That is the bargain we make by existing in a quantum universe. But the false vacuum also teaches us curiosity. If the universe is metastable, then understanding why it has not decayed yet becomes one of the most important questions in physics. Solving that puzzle could reveal new particles, new forces, new dimensions of reality. It could lead to a complete theory of quantum gravity, the holy grail of theoretical physics. So we keep searching. We build bigger colliders. We measure the Higgs field more precisely. We look for signs of new physics that might stabilize or destabilize the vacuum. And with every measurement, we learn a little more about the nature of reality. The marble is still in its valley, for now. But every time a cosmic ray strikes the atmosphere, every time a quantum fluctuation ripples through the void, there is a vanishingly small chance that the marble will tip. And on the day it does, the universe will discover what lies in the deeper valley below. That is the theory cosmologists do not like to talk about at parties. Theory 2. The great attractor is dragging us towards something we cannot see. You are moving right now, not just because Earth spins on its axis, or because it orbits the sun, or because the sun orbits the center of the Milky Way. You are moving because something immense, something hidden, is pulling you and every galaxy in your neighborhood toward itself at more than 2 million kilometers per hour. Astronomers call it the Great Attractor. In the 1970s, scientists began creating the first large-scale maps of the universe. They measured the redshifts of thousands of galaxies, expecting to see a uniform pattern consistent with the expansion of space since the Big Bang. What they found instead was a flow, a vast river of galaxies streaming in one direction. Hundreds of galaxies, including our own Milky Way, were moving toward a specific point in the southern sky, in the direction of the constellations Norma and Triangulum Australe. At first, researchers thought it might be an error, but more observations confirmed it. After accounting for the expansion of the universe, the Milky Way has a peculiar velocity, a motion not explained by cosmic expansion alone, of approximately 600 kilometers per second. That is more than 2 million kilometers per hour, all in the same direction. The entire local group of galaxies is being pulled towards something roughly 220 million light-years away. But when astronomers looked in that direction, they saw nothing. The Great Attractor lies directly behind the plane of our own Milky Way, in a region of sky known as the zone of avoidance. Dense clouds of gas, dust, and countless stars in our galactic disk block our view of the distant universe in that direction. Looking toward the Great Attractor with an optical telescope is like trying to see a candle flame through a thick curtain of smoke. We can infer its presence from the motion of galaxies around it, but we cannot observe it directly. So astronomers turn to other wavelengths. Infrared telescopes can pierce through dust. Radio telescopes can detect neutral hydrogen gas in distant galaxies. X-ray observatories can spot the hot gas between galaxy clusters. Using these tools, researchers began to peel back the veil. In the 1990s and 2000s, surveys like the Parkes HY survey and the Clusters in the Zone of Avoidance project detected hundreds of hidden galaxies in the Forbidden Zone. 51% of obscured sources revealed themselves through neutral hydrogen emissions. What they found was not a single massive object, but a complex web of galaxy clusters. At the heart of the Great Attractor region lies the Norma Cluster, a massive concentration of galaxies roughly 320 million light-years away. Surrounding it are filaments of galaxies, walls of matter stretching across hundreds of millions of light-years. Together, these structures form a gravitational focal point, a basin in the cosmic landscape toward which matter flows like water down a slope. The Great Attractor is not an object. It is a region of space, a node in the cosmic web where gravity converges. But the story does not end there. In 2014, astronomers used a new technique to map the large-scale structure of the universe. Instead of just measuring where galaxies are located, they tracked the direction of their motion, their peculiar velocities. By mapping these flows, they discovered something stunning. The Great Attractor is just one part of a much larger structure called the Laniakea supercluster. The name means immeasurable heaven in Hawaiian, and it spans more than 500 million light-years. Our Milky Way, the Great Attractor, and more than 100,000 other galaxies all belong to Laniakea, bound together by gravity into a single vast system. And Laniakea itself is moving. Beyond the Great Attractor lies an even more massive structure, the Shapley supercluster, located about 650 million light-years away. With a mass estimated at over 10,000 times that of the Milky Way, the Shapley supercluster exerts a gravitational pull so strong that it influences the motion of galaxies across hundreds of millions of light-years. The Great Attractor, it turns out, is being pulled toward the Shapley supercluster, and we, in turn, are being pulled along with it. We are not just passengers in an expanding universe. We are participants in a vast cosmic flow, a current that carries galaxies across unimaginable distances, all driven by the invisible hand of gravity. But here is where it gets strange. According to the standard model of cosmology, the universe should be expanding uniformly in all directions. On the largest scales, matter should be distributed evenly, and there should be no preferred direction of motion. Yet observations reveal that galaxies within hundreds of millions of light-years are moving in coherent flows, streaming toward massive overdensities like the Great Attractor and the Shapley supercluster. These flows suggest that the universe is not as smooth as we thought. There are lumps, voids, and currents on scales far larger than our theories comfortably accommodate. Recent measurements have made the problem more acute. In 2025, data from the Cosmic Flows 4 survey measured peculiar velocities out to 173 megaparsecs with amplitudes of 428 kilometers per second. But there is a tension. The observed flows are slightly larger than the standard cosmological model predicts. The discrepancy is small, only 0.11%, but it is measurable. Either there are uncertainties in the data that we have not accounted for, or there is something wrong with our understanding of how structure forms in the universe. Some physicists have proposed alternative explanations. Modified Newtonian dynamics, or MOND, suggests that gravity behaves differently on large scales than we currently believe. Others point to exotic dark matter structures or hidden dimensions of space-time. A few even speculate that the Great Attractor's pull could be evidence of a deeper flaw in our cosmological models, a crack in the foundation of the Big Bang theory itself. But most scientists favor a simpler explanation. we do not yet fully understand dark matter and dark energy. Dark matter, which makes up approximately 85% of the matter in the universe, does not emit, absorb, or reflect light. We can only detect it through its gravitational effects. The Great Attractor region likely contains vast amounts of dark matter, concentrating gravity in ways we cannot directly observe. Dark energy, the mysterious force driving the accelerated expansion of the universe, may also play a role. If dark energy varies in strength across space, it could create asymmetries in the cosmic flow, pushing and pulling galaxies in unexpected ways. Recent observations from the Dark Energy Spectroscopic Instrument, or DESI, have added a new twist. In 2024, DESI released data suggesting that dark energy may not be constant over time. If dark energy evolves, it could explain some of the anomalies in large-scale structure, including the unexpectedly strong flows toward the Great Attractor. The jury is still out, but the data point toward a universe that is more dynamic, more complex than we imagined. So why is the Great Attractor terrifying? Because it reveals how little we understand about the forces shaping our cosmic home. We cannot see it directly. We can only infer its existence from the motion of galaxies, like sailors feeling a current beneath their ship without knowing what lies in the depths below. We know that something with the mass equivalent of tens of thousands of Milky Ways is pulling us toward it. We know that it is part of a structure spanning 500 million light-years, but we do not know what it truly is, or what we might find if we could see it clearly. And there is another unsettling possibility. If the Great Attractor is not alone, if there are other, even larger structures lurking in regions of the universe we have not yet mapped, then our picture of the cosmos is fundamentally incomplete. We may be sailing through a universe filled with hidden giants, gravitational leviathans whose influence we feel but whose nature we cannot fathom. Every time we peer deeper into space, we find something unexpected. What other mysteries are hiding in the zones we cannot see? The Great Attractor is a reminder that the universe does not reveal its secrets easily. It forces us to confront the limits of our knowledge, the boundaries of our instruments, and the humbling reality that even after centuries of astronomy, we are still mapping the edges of the unknown. We are being pulled toward something we do not understand, at speeds we cannot control, through a cosmos that may be stranger than we ever imagined. And we are moving faster every second. Theory 3. Rogue black holes are wandering through the galaxy. Right now, black holes are supposed to stay in their place. At the heart of nearly every large galaxy, a supermassive black hole sits like a cosmic anchor, holding the galaxy together with its immense gravity. Smaller black holes, formed from the collapse of massive stars, orbit within the galactic disk, bound to their original neighborhoods. This is the textbook picture. This is what we expect. But the universe does not always follow the textbook. In 2025, astronomers using the Zwicky Transient Facility detected a flash of light in a galaxy 600 million light-years away. It was not a supernova. Supernova cool and redden as they fade. This flash remained hot and blue for months, consistent with a tidal disruption event, a star torn apart by a black hole's gravity. But there was something wrong with its location. The flash was not at the center of the galaxy where supermassive black holes reside. It was more than 2,600 light-years away from the galactic core, drifting in the outskirts. Hubble Space Telescope images confirmed what the data suggested: a massive black hole wandering through its host galaxy, devouring a star that strayed too close. This was the first optical detection of a rogue supermassive black hole caught in the act of feeding. Astronomers had long theorized that wandering black holes should exist. When two galaxies collide and merge, their central black holes can be thrown off course by gravitational interactions. In a three-body system, two black holes and a third massive object, the dynamics become chaotic. One black hole can be flung out of the galactic center, sent careening through the galaxy at hundreds of kilometers per second. Or, if a small satellite galaxy merges with a larger one, the smaller galaxy's black hole might be left stranded, orbiting far from the new galactic core. But proving that such rogues exist has been difficult. Black holes are invisible. They do not emit light. The only way to find them is to catch them in the act of feeding, when a star wanders too close and gets shredded by tidal forces. The burst of light from such a tidal disruption event lasts for weeks or months and then fades. If you are not looking at the right place at the right time, you miss it. The Zwicky Transient Facility scans the northern sky every few nights, detecting hundreds of transient flashes each year. Most of them are supernovae. A few are tidal disruption events. But until 2025, all the tidal disruption events detected were located at the centers of galaxies, where supermassive black holes are expected to reside. The discovery of a tidal disruption event far from a galactic core was the first direct evidence that massive black holes can wander, and it is probably not alone. In September 2025, astronomers reported another wandering black hole in a dwarf galaxy 230 million light-years away. This one was even more unusual. Not only was it offset from the galactic center by nearly a kiloparsec, roughly 3,000 light-years, but it was actively accreting matter and producing radio jets. Jets are streams of particles accelerated to nearly the speed of light, powered by the intense magnetic fields around a feeding black hole. The jets from this rogue black hole stretched for 7.2 light-years, a clear signature of an active galactic nucleus. But it was not at the nucleus. It was wandering through the galactic disk. Radio observations revealed temperatures exceeding 1 billion degrees Celsius. Decades of archival data showed that the region brightened and dimmed over time, characteristic of a black hole that feeds in bursts. The black hole's mass was estimated at 300,000 times the mass of the Sun, an intermediate mass black hole, a type that has eluded astronomers for decades. And it was roaming. These discoveries raise unsettling questions. How common are rogue black holes? If 2 have been found in recent surveys, how many more are out there, drifting unseen through the void? Theoretical predictions suggest that wandering black holes should be numerous, especially in galaxies that have experienced mergers. Every collision between galaxies has the potential to eject 1 or more black holes from the galactic center. Over billions of years, the number of rogues could be substantial, and they are almost impossible to detect. A black hole that is not feeding produces no light, no radiation, no signal. It is a gravitational ghost, invisible to our telescopes. The only way we know it is if a star happens to wander too close, an event that occurs on average once every 30,000 years for a given wandering black hole. That means for every rogue we detect, there could be thousands or millions that remain hidden. What if one is nearby? The Milky Way has almost certainly experienced mergers in its past. Smaller galaxies have fallen into our gravitational well, their stars absorbed into our galactic halo. If those smaller galaxies had their own central black holes, where are they now? Some may have sunk to the Milky Way's core and merged with our own supermassive black hole, Sagittarius A star, but others may have been flung out into the galactic halo, wandering through the outskirts of our galaxy. In 2022, astronomers confirmed the first lone black hole in the Milky Way, detected through a technique called gravitational microlensing. When a black hole passes in front of a distant star, the black hole's gravity bends the star's light, creating a temporary brightening. By measuring the duration and shape of the brightening, astronomers can infer the mass and distance of the lensing object. The black hole they found was drifting through the constellation Sagittarius, roughly 5,000 light-years from Earth. It had no companion star, no accretion disk, no light. Just gravity, moving silently through the void. This discovery proved that isolated black holes exist in our galaxy, and if one has been found, there are likely many more. Estimates suggest there could be tens of millions of stellar mass black holes in the Milky Way, most of them invisible. The European Space Agency's Gaia telescope is currently mapping the positions and motions of billions of stars in our galaxy. In 2025, Gaia is expected to release lensing data that could contain evidence for dozens of additional black holes. The Vera C. Rubin Observatory, which began its 10-year survey in 2026, will scan the southern sky every few nights, catching transient events like tidal disruptions. NASA's Nancy Grace Roman Space Telescope, set to launch in 2027, will also search for microlensing events caused by rogue black holes. Within the next decade, we may discover that wandering black holes are not rare anomalies but common inhabitants of the cosmos. And that raises a terrifying possibility. What happens if a rogue black hole passes through our solar system? The probability is extraordinarily low. Space is vast and black holes are small. Even a black hole 10 times the mass of the Sun has an event horizon only 60 kilometers across. For it to come close enough to Earth to cause significant gravitational disruption, it would have to pass within a few astronomical units, the distance from Earth to the Sun. The odds of such an event occurring in the lifetime of our solar system are effectively zero, but effectively zero is not the same as zero. If a stellar mass black hole were to pass through the outer solar system, it would gravitationally perturb the orbits of planets. Neptune, Uranus, and the outer worlds could be nudged into eccentric orbits, destabilizing the delicate gravitational balance that has persisted for billions of years. If the black hole passed closer, through the asteroid belt or the inner solar system, the effects would be catastrophic. Asteroids could be flung toward Earth, planetary orbits could be altered, the Sun itself could be disturbed. And if a supermassive black hole, millions or billions of times the mass of the Sun, were to wander into our neighborhood, the destruction would be total. The Milky Way would be torn apart. Stars would be ripped from their orbits. Entire solar systems would be spaghettified and consumed. But such an event, while theoretically possible, is almost inconceivably unlikely. Supermassive black holes move slowly through intergalactic space, and the distances between galaxies are so vast that close encounters are rare. The real danger is not a direct collision. The real danger is that we do not know where these black holes are. They could be anywhere, drifting through the galactic halo, lurking in the spaces between stars, moving silently through the void. We cannot see them unless they feed, and they spend most of their time starving. Every few tens of thousands of years, one might tear apart a star and reveal its location. The rest of the time, they are invisible. This is not a distant, abstract threat. This is a feature of our galaxy, right now, today. Somewhere out there, a black hole is wandering. It has been wandering for billions of years, a gravitational predator moving through the darkness. And we have no way of knowing where it is. Theory 4. Dark energy may not be constant, and that changes everything. For more than 2 decades, cosmologists have operated under a simple assumption. Dark energy, the mysterious force driving the accelerated expansion of the universe, is constant. It does not change over time. It does not vary from place to place. It is, in the language of physics, a cosmological constant, a fixed property of empty space itself, permeating the universe uniformly and eternally. But in 2024, that assumption began to crack. The Dark Energy Spectroscopic Instrument, or DESI, is a global collaboration that maps the three-dimensional structure of the universe by measuring the redshifts of tens of millions of galaxies. In April 2024, DESI released its first-year results, and they contained a surprise. The data suggested that dark energy might not be constant after all. Instead, it could be evolving, its density changing as the universe ages. If true, this would overturn our entire understanding of cosmology. Dark energy was first discovered in the late 1990s, when 2 independent teams of astronomers measured the distances to distant supernovae. They expected to find that the expansion of the universe was slowing down, pulled back by the gravity of all the matter it contains. What they found instead was the opposite. The universe is expanding faster now than it was in the past. The expansion is accelerating. To explain this, cosmologists invoked a cosmological constant, often represented by the Greek letter lambda. Lambda is Einstein's old idea, resurrected from the dustbin of history. In the 1920s, Einstein added a term to his equations of general relativity to keep the universe static, as was believed at the time. When Edwin Hubble discovered that the universe is expanding, Einstein reportedly called the cosmological constant his biggest blunder. But in the late 1990s, it turned out he was right after all, just for the wrong reason. The cosmological constant is not there to keep the universe static. It is there to make it accelerate. For decades, observations supported the idea of a constant dark energy. Measurements of the cosmic microwave background radiation, the afterglow of the Big Bang, agreed with supernova data. The universe seemed to be about 70% dark energy, 25% dark matter, and 5% ordinary matter. And the dark energy density appeared to be unchanging, but DESI's data suggested otherwise. By analyzing the clustering of galaxies at different epochs in cosmic history, DESI researchers found hints that the equation of state for dark energy, a number that describes how its density changes with the expansion of the universe, might not be exactly -1, as a cosmological constant would require. Instead, it could be slightly different, varying over time. The statistical significance was not overwhelming, but it was enough to raise eyebrows. Follow-up analyses using independent methods confirmed the result. Dark energy, it seems, might be dynamic. This finding was echoed by Chinese and international astronomers in 2025. A team led by researchers at the National Astronomical Observatories of the Chinese Academy of Sciences combined DESI's measurements with data from supernovae and the cosmic microwave background. Their analysis showed that the equation of state for dark energy changes as the universe evolves. The result was statistically robust, and it aligned with DESI's earlier conclusions. What does this mean? If dark energy is not constant, then it is not a cosmological constant. It is something else. Physicists have proposed several alternatives. One possibility is that dark energy is not a property of space itself, but a field, like the Higgs field, that pervades the universe. This hypothetical field, sometimes called quintessence, could vary in strength over time, driving the expansion at different rates during different epochs. Another possibility is that dark energy is an emergent phenomenon, arising from the interactions between dark matter and ordinary matter. A third possibility is that our understanding of gravity is wrong, and what we call dark energy is actually a modification of general relativity on cosmic scales. Each of these possibilities has profound implications. If dark energy is a field, then it has a history. It had a value in the early universe, a value now, and will have a different value in the future. This opens the door to understanding why dark energy has the strength it does today. It also raises the question of what will happen next. Will dark energy continue to strengthen, driving the universe to expand faster and faster until galaxies are torn apart? Or will it weaken, allowing gravity to slow the expansion? Or could it even reverse, causing the universe to contract in a big crunch? If dark energy is an interaction between dark matter and ordinary matter, then the cosmic web of galaxies, the filaments and voids that make up the large-scale structure of the universe, plays an active role in shaping the expansion. This would tie together two of the greatest mysteries in cosmology, dark matter and dark energy, into a single framework. It would suggest that the universe is more interconnected than we thought, with the invisible scaffolding of dark matter influencing not just the motion of galaxies but the very fabric of space-time itself. And if gravity is modified, then general relativity, one of the most successful theories in the history of physics, needs to be revised. This would be a revolution comparable to the shift from Newtonian mechanics to Einstein's relativity. It would require us to rethink everything we know about black holes, gravitational waves, and the structure of space-time. None of these options are comforting. They all imply that the universe is more complex, more unpredictable, and more mysterious than our current models allow. And they all suggest that the future of the cosmos is uncertain. The DESI collaboration is continuing to collect data. Year 2 and Year 3 results are expected in 2025 and 2026. The European Space Agency's Euclid mission, launched in 2023, is also mapping the universe's structure and measuring dark energy with unprecedented precision. NASA's Nancy Grace Roman Space Telescope, set to launch in 2027, we'll observe millions of supernovae in galaxies, providing another independent test of dark energy's behavior. Within the next few years, we will know whether dark energy is truly evolving or whether the hints we see now are statistical flukes. But the possibility that dark energy is changing forces us to confront an uncomfortable truth. We do not understand the force that dominates the universe. 70% of the cosmos is made of something we cannot explain. We have given it a name, dark energy, but we do not know what it is, where it comes from, or what it will do next. We have built a cosmological model that fits the data, but the data are now suggesting that the model is incomplete. And if the model is wrong, then our predictions about the future of the universe are wrong too. Will the expansion accelerate forever, driving galaxies beyond the reach of our telescopes, leaving future civilizations in an empty, isolated cosmos? Or will dark energy decay, allowing the universe to coast or even reverse? Could the universe cycle through phases of expansion and contraction, an endless rhythm of birth and death? We do not know. And that, more than anything, is what makes dark energy terrifying. It is not just that it is mysterious, it is that it is in control. It shapes the fate of the cosmos, determines the ultimate destiny of every galaxy, every star, every atom. And we are only now beginning to realize that we might have been wrong about it all along. Theory 5. Boltzmann brains. You might not be real. Close your eyes for a moment. Picture your earliest memory. Maybe it is a birthday party, a family trip, a moment of childhood wonder. You remember it clearly. You can see the faces, hear the voices, feel the emotions. That memory is real. It happened. Or did it? According to a disturbing implication of statistical physics, there is a non-zero probability that you are not a product of billions of years of cosmic evolution. You are not the descendant of countless generations of life forms that struggled and adapted on a planet orbiting a star in a galaxy formed from the debris of the Big Bang. You are a Boltzmann brain, a disembodied consciousness that spontaneously fluctuated into existence from the quantum vacuum, complete with false memories of a past that never happened. This is not a joke. This is a serious problem in cosmology. The idea is named after Ludwig Boltzmann, the 19th century physicist who developed the statistical theory of thermodynamics. Boltzmann's work explained why entropy, the measure of disorder in a system, always increases over time. A shattered glass does not spontaneously reassemble. A gas does not compress itself into a corner. Heat flows from hot to cold, never the reverse. These are manifestations of the second law of thermodynamics, one of the most fundamental principles in physics. But Boltzmann realized something troubling. If you wait long enough, even the most improbable events will eventually happen. Imagine a gas in a box. Most of the time, the gas molecules are spread evenly throughout the box in a state of maximum entropy, but occasionally, by random chance, the molecules will cluster together in one corner, creating a temporary region of low entropy. The probability of this happening is extraordinarily small, but if you wait long enough, it will occur. Boltzmann calculated that given enough time, any configuration of matter, no matter how unlikely, will eventually arise from random fluctuations. This applies to brains too. A human brain is an extraordinarily complex structure with roughly 86 billion neurons connected by trillions of synapses. The probability that such a structure would spontaneously assemble from random fluctuations in the vacuum is astronomically low, but it is not zero. And in an infinite or near-infinite universe that lasts forever, even the most improbable events become certain. Now here is the problem. If the universe is in a state of thermal equilibrium, or approaching equilibrium, then over vast timescales, fluctuations will produce all sorts of structures. Some fluctuations will produce entire galaxies, some will produce solar systems, some will produce planets with biospheres and civilizations, and some will produce just a brain, floating in empty space, with neurons firing in patterns that create the illusion of consciousness and memory. Which is more likely, A fluctuation that produces an entire observable universe with 13.8 billion years of history, or a fluctuation that produces just a brain with the same memories and experiences but without the universe around it? The answer, according to Boltzmann's logic, is clear. The brain. Smaller fluctuations are exponentially more probable than larger ones. A fluctuation that creates a single brain requires far less organization, far less borrowing of energy from the vacuum, than a fluctuation that creates an entire cosmos. If the universe lasts long enough, Boltzmann brains should vastly outnumber normal brains like ours. In fact, statistically speaking, you are far more likely to be a Boltzmann brain than a real human being. This is the Boltzmann brain paradox. If the paradox is true, then most of your memories are false. You never had a childhood. You were never born. The universe you think you observe does not exist. You are a random fluctuation in the void, destined to dissolve back into the vacuum in the next instant. And the same is true for everyone you know, every thought you have, every word you read. Physicists hate this conclusion. Sean Carroll, a cosmologist at the California Institute of Technology, has stated bluntly, "We're not arguing that Boltzmann brains exist. We're trying to avoid them." The Boltzmann brain scenario is treated as a reductio ad absurdum, a sign that something is wrong with our understanding of the universe. If a cosmological theory predicts that Boltzmann brains should be common, that theory is considered falsified. But how do we avoid Boltzmann brains? One way is to ensure that the universe has a finite lifetime. If the universe does not last forever, then there is not enough time for low-probability fluctuations like Boltzmann brains to become common. The universe would end before the improbable becomes probable. But our current best theories do not provide such an ending. The universe appears to be accelerating, driven by dark energy. If dark energy is constant, the universe will expand forever, eventually reaching a state similar to thermal equilibrium. And in that eternal empty future, Boltzmann brains would inevitably appear. Another way to avoid Boltzmann brains is to invoke quantum mechanics. In 2024, researchers at the Santa Fe Institute examined the Boltzmann brain problem and found that many standard arguments involve circular reasoning. The paradox, they argued, arises from a tension in how we treat time and entropy in statistical physics. Depending on the interpretation of quantum mechanics, Boltzmann brains may or may not be a problem. For example, in the many worlds interpretation of quantum mechanics, the universe constantly branches into parallel realities. Some physicists, including Sean Carroll, have suggested that in a many worlds framework, the Boltzmann brain problem dissolves. The formation of the universe itself is a quantum fluctuation, but it is not a classical random fluctuation in a thermal bath. The quantum branching structure prevents Boltzmann brains from dominating. In de Broglie-Bohm mechanics, also known as pilot wave theory, the Boltzmann brain paradox is similarly disallowed. The deterministic evolution of quantum states in this interpretation does not allow for the kind of random fluctuations that would produce isolated brains. But these solutions depend on accepting specific interpretations of quantum mechanics, and not all physicists agree on which interpretation is correct. Another proposed solution involves the Higgs field. If the vacuum is metastable, if it can decay into a lower energy state, then the universe might not last forever. Vacuum decay would bring an end to the current era of physics, preventing the eternal thermal equilibrium required for Boltzmann brains to form. Some researchers have calculated that to avoid Boltzmann brains, the vacuum decay timescale should be on the order of the current age of the universe. If the top quark mass is approximately 178 billion electron volts, the vacuum would decay before Boltzmann brains become probable. But this solution is not comforting. It trades one terrifying scenario, being a Boltzmann brain, for another, the universe ending in a vacuum decay catastrophe. The Boltzmann brain problem forces us to confront deep questions about the nature of reality. How do we know that our memories are real? How do we know that the universe we observe is the result of a genuine history rather than a random fluctuation? The answer, unsettlingly, is that we cannot know for certain. All we can do is assume that our memories are reliable, that the laws of physics are consistent, and that the universe has the history cosmology suggests. But these are assumptions, not proven facts. The Boltzmann brain paradox highlights a fundamental tension in physics. On the one hand, we want our theories to be consistent with thermodynamics, which tells us that entropy always increases. On the other hand, we want our theories to predict a universe where we are typical observers, not random flukes. Reconciling these two demands requires careful reasoning and perhaps new physics that we have not yet discovered. Some physicists argue that the Boltzmann brain problem is a sign that the concept of an eternal universe is wrong. Others argue that it reveals flaws in how we apply statistical reasoning to cosmology. Still others suggest that it is a quirk of our current models, and future theories will resolve it naturally. But until we have a complete theory of quantum gravity, until we understand the ultimate fate of the universe, and until we know whether dark energy is constant or evolving, the Boltzmann brain problem remains unsolved. And every time you remember something, there is a tiny, unsettling voice in the back of your mind that asks, did this really happen? Or am I just a fluctuation in the void? Theory 6. The heat death of the universe. Inevitable silence. Imagine a universe where nothing moves. Stars have burned out. Black holes have evaporated. Galaxies have drifted so far apart that no light from one can ever reach another. The temperature everywhere is the same, a fraction of a degree above absolute zero. There is no energy left to do work, no gradients to drive processes, no differences to exploit. Everything is in perfect thermal equilibrium. This is the heat death of the universe. It is not a sudden catastrophe like a big crunch or a vacuum decay. It is a slow, inexorable slide toward equilibrium, driven by the second law of thermodynamics. Entropy, the measure of disorder, always increases in an isolated system. And the universe, as far as we can tell, is an isolated system. There is nothing outside it, no external source of energy, no way to reset the clock. Every process that occurs, every star that burns, every galaxy that forms, every thought that crosses your mind, increases the total entropy of the cosmos. And entropy can only go one way, up. The idea of heat death dates back to the 1850s, when William Thomson, later known as Lord Kelvin, extrapolated the laws of thermodynamics to the universe as a whole. He reasoned that if energy is constantly being converted from useful forms, like the motion of planets or the light of stars, into less useful forms, like heat radiated into empty space, then eventually all the energy in the universe will be evenly distributed. There will be no more temperature differences, no more chemical reactions, no more life. The universe will reach a state of maximum entropy, and nothing will ever happen again. This vision troubled Kelvin and his contemporaries. It implied that the universe had a beginning and would have an end. It suggested that all the complexity we see, the stars, the galaxies, the intricate structures of life, are temporary phenomena, doomed to dissolve into featureless uniformity. For decades, the heat death scenario was one possible fate among many. The universe might recollapse in a big crunch. It might cycle through endless phases of expansion and contraction. It might exist in a steady state, with new matter constantly being created to replace what drifts away. But in the late 1990s, observations of distant supernovae changed everything. The universe is not just expanding, it is accelerating. The most likely explanation is dark energy, a repulsive force that pushes the fabric of space apart. If dark energy is constant, the universe will expand forever. And if it expands forever, it will reach heat death. Here is how it would unfold. Over the next 100 billion years, galaxies will continue to drift apart. The expansion of space will carry them beyond the reach of one another's light. Future observers in distant galaxies will look out into a dark, empty sky with no hint that other galaxies ever existed. Within our own galaxy, stars will continue to burn for trillions of years, but eventually they will run out of fuel. The smallest stars, the red dwarfs, will shine for 10 trillion years before fading into cold, dead remnants. After the last star dies, the universe will enter what cosmologists call the degenerate era. Matter will consist mostly of white dwarfs, neutron stars, and black holes. These objects will slowly decay. White dwarfs will cool to black dwarfs, objects so cold they emit no light. Neutron stars will collapse or evaporate. Black holes will be the last remnants of the old universe, but even they will not last forever. Stephen Hawking discovered in the 1970s that black holes are not truly black. They emit radiation due to quantum effects near the event horizon, a process now known as Hawking radiation. This radiation causes black holes to lose mass very slowly. A black hole with the mass of the Sun would take 10 to the power of 67 years to evaporate. A supermassive black hole with 1 billion solar masses would take 10 to the power of 100 years. But eventually, even the largest black holes will disappear, and then there will be nothing left but a dilute gas of photons and leptons spread across an ever-expanding universe. The temperature will drop to a fraction of a degree above absolute zero. Energy will be distributed so evenly that no process can extract work from it. The universe will be in perfect thermal equilibrium. This is the heat death. Or is it? Some physicists point out that the concept of heat death assumes the universe is a closed system, in equilibrium, and governed by classical thermodynamics. But the universe is expanding, driven by dark energy, and dominated by quantum mechanics on the smallest scales. Does thermodynamics even apply in such a context? Max Planck, one of the founders of quantum theory, wrote that the phrase entropy of the universe has no meaning because the universe admits no accurate definition. Walter Grandy, a physicist at the University of Wyoming, argued that we cannot associate an entropy with the universe because it has never been in equilibrium. If the universe is not in equilibrium, then the second law of thermodynamics, as traditionally formulated, may not apply. But even if we set aside these objections, there are other possibilities. The universe could undergo a second inflationary epoch, a burst of rapid expansion that resets the entropy clock. This is speculative, but some models of dark energy allow for it. Or the vacuum could decay into a lower energy state, as discussed earlier, ending the current era of physics and beginning a new one with different laws. In that case, heat death would be replaced by vacuum decay, which is arguably worse. Another possibility is that the universe is cyclic. In cyclic cosmologies, the universe undergoes endless phases of expansion and contraction, with each cycle beginning in a big bang and ending in a big crunch. Entropy might be reset at the start of each cycle, preventing heat death, but cyclic models face serious theoretical challenges, and most cosmologists consider them unlikely. The most widely accepted view is that the universe will indeed reach heat death, but not for an unimaginably long time. The timescales involved are so vast that they beggar comprehension. 10 to the power of 100 years is a 1 followed by 100 zeros. For comparison, the current age of the universe is only about 10 to the power of 10 years. Heat death is not an immediate threat. It is not even a distant threat. It is a cosmological inevitability that lies so far in the future that it might as well be infinity. But it is still real. And that is what makes it terrifying. Not because it will affect us, or our descendants, or even the distant civilizations that might arise billions of years from now, but because it reminds us that the universe is finite. Everything that exists today, every star, every planet, every thought, every creation, is temporary. The structures we see around us, the complexity and beauty of the cosmos, are not permanent features of reality. They are transient patterns in a universe sliding toward disorder. In the end, there will be nothing. No light, no heat, no motion. Just an infinite expanse of cold, dark, empty space, forever. The universe will not end with a bang or a whimper. It will end with silence. Theory 7. The Hubble tension. Our measurements do not agree. There is a number that should be simple. It tells us how fast the universe is expanding. Measure the distance to a galaxy, measure how fast it is moving away, and you get the expansion rate, a value called the Hubble constant, represented as h0. Every cosmologist should get the same answer, regardless of their method. The universe has one expansion rate, not two, but we are getting two different answers, and they do not match. This is the Hubble tension, and it is one of the most troubling puzzles in modern cosmology. The first method uses the cosmic microwave background, the afterglow of the Big Bang. When the universe was 370,000 years old, it was hot and dense, filled with a plasma of electrons and photons. As the universe expanded and cooled, electrons combined with protons to form neutral hydrogen atoms, and photons were released. Those photons have been traveling through space ever since, and we can see them today as a faint microwave glow in every direction of the sky. The cosmic microwave background is extraordinarily uniform. Its temperature varies by only 1 part in 100,000 from place to place. But those tiny variations contain a wealth of information. By measuring the size and distribution of hot and cold spots in the microwave sky, cosmologists can infer the density of matter and dark energy, the curvature of space, and the expansion rate of the universe. In 2018, the Planck satellite produced the most precise measurement of the cosmic microwave background to date. From that data, cosmologists calculated the Hubble constant, 67.4 kilometers per second per megaparsec, with an uncertainty of only half a kilometer per second per megaparsec. This number means that for every megaparsec, roughly 3.3 million light-years, of distance between us and a galaxy, the expansion of space carries that galaxy away at 67.4 kilometers per second. It is a prediction based on the standard cosmological model, which assumes that the universe has been expanding smoothly since the Big Bang, driven by dark matter and dark energy. The second method uses distance measurements to nearby galaxies. Astronomers observe a type of star called a Cepheid variable, whose brightness pulsates in a regular pattern. The period of the pulsation is directly related to the star's intrinsic brightness. By measuring the period, astronomers can determine how bright the star should be. By comparing that to how bright it appears from Earth, they can calculate the distance. Using Cepheid variables, astronomers calibrate the distances to galaxies and then observe Type 1 supernovae, exploding white dwarfs that serve as standard candles because they always have roughly the same intrinsic brightness. This method, pioneered by Wendy Friedman and her colleagues, has been refined over decades. In 2024, the Chicago Carnegie Hubble program, led by Friedman, produced a new measurement of the Hubble constant using an alternative method called the tip of the red giant branch. The result, 70 kilometers per second per megaparsec, with an uncertainty of roughly 1 kilometer per second per megaparsec. That is 2.6 kilometers per second per megaparsec, faster than the cosmic microwave background prediction. And the discrepancy is statistically significant. When two measurements differ by more than 5 times their combined uncertainties, physicists call it a 5 sigma tension, strong evidence that something is wrong. The Hubble tension is now at more than 4 sigma, depending on which data sets are compared. Some recent measurements have pushed the local expansion rate even higher, to 73 or 76 kilometers per second per megaparsec, deepening the crisis. This is not a small problem. It is not a minor calibration issue or a subtle systematic error. It is a fundamental disagreement about how fast the universe is expanding. And after years of checking and rechecking the data, the tension has not gone away. If anything, it has gotten worse. So what is going on? There are 3 possibilities. First, there could be unidentified systematic errors in one or both methods. Perhaps the Cepheid calibration is off. Perhaps the cosmic microwave background analysis relies on incorrect assumptions. Second, the tension could be a statistical fluke, a rare coincidence that will disappear with more data. Third, and most unsettling, the tension could be real, a sign that our standard cosmological model is wrong. Most cosmologists do not think the tension is a statistical fluke. The odds are too low, and the tension has persisted across multiple independent studies. Systematic errors are possible, but both methods have been scrutinized extensively, and no obvious mistakes have been found. That leaves the third possibility: new physics. What kind of new physics could resolve the Hubble tension? One idea is that dark energy is not constant. If dark energy was weaker in the early universe and has strengthened over time, it could make the universe expand faster now than the cosmic microwave background predicts. This aligns with the DESI observations discussed earlier, which suggest that dark energy may be evolving. If dark energy is dynamic, the Hubble tension could be the first hint of its variability. Another idea is that dark matter interacts with dark energy. In a model called interacting dark energy, or IDE, dark matter can transfer energy to dark energy or vice versa. This interaction could affect the expansion rate in ways that reconcile the cosmic microwave background and local measurements. Some researchers have shown that the IDE model can alleviate not only the Hubble tension but also another discrepancy called the S8 tension, which concerns how clumpy the universe is. A third possibility is that there is a new type of particle or field that affects the early universe. For example, if there were additional relativistic particles, sometimes called dark radiation, present during the cosmic microwave background era, they could alter the expansion rate and shift the Hubble constant prediction. Such particles would have to be light, weakly interacting, and present only in the very early universe. A fourth possibility is that our understanding of gravity is incomplete. Modified gravity theories, like modified Newtonian dynamics or extensions of general relativity, could produce different expansion rates on different scales. If gravity behaves differently on cosmic scales than we expect, it could explain why the Hubble constant measured locally does not match the value inferred from the cosmic microwave background. Each of these ideas has problems. None fits all the data perfectly, and some require invoking entirely new physics that we have never observed. But the alternative, accepting that our standard cosmological model is fundamentally wrong, is even more troubling. The Hubble tension is not going away. In 2025, a new study of the Coma cluster, a massive galaxy cluster 320 million light-years away, provided the most precise distance measurement ever for that cluster. The results strengthened the tension, pushing the local Hubble constant even higher. Wendy Friedman was named one of Nature's top 10 science leaders of 2024 for her work on this problem, a recognition of how central it has become to cosmology. Future observations will provide more tests. The James Webb Space Telescope is measuring Cepheid variables in distant galaxies, extending the distance ladder to new limits. The Vera C. Rubin Observatory will observe thousands of supernovae, refining the local expansion rate. The Nancy Grace Roman Space Telescope will map the large-scale structure of the universe, providing another independent measurement. But what if all these observations confirm the tension? What if, after all the checks and cross-checks, we are left with an irreconcilable disagreement? Then we will have to rethink cosmology. The standard model, lambda CDM as it is called, has been extraordinarily successful. It explains the cosmic microwave background, the large-scale structure of galaxies, the abundances of light elements, and the accelerated expansion of the universe. It is one of the triumphs of 20th century physics. But if the Hubble tension is real, lambda CDM is incomplete. There is something missing, some piece of the puzzle we have not yet found. And that is terrifying because it means we do not understand the universe as well as we thought. Imagine building a bridge based on incomplete physics. You calculate the stresses, the loads, the materials needed, all based on your best understanding of mechanics. And then, halfway through construction, you discover that your equations are wrong. The bridge does not behave the way you predicted. What do? Do you tear it down and start over? Or do you patch it and hope for the best? Cosmology is facing a similar dilemma. The bridge we have built, our model of the universe, does not quite work. The measurements do not line up, and we have to decide, do we adjust the model, or do we rebuild it from scratch? The Hubble tension is not just a number. It is a crack in the foundation of cosmology, and the longer it persists, the wider it gets. Theory 8. Phantom dark energy could rip apart the universe. Dark energy drives the accelerated expansion of the universe. We know it is there because we can measure its effects, but we do not know what it is, and depending on what it turns out to be, the future of the universe could be very different. If dark energy is a cosmological constant, a fixed property of empty space, the universe will expand forever, eventually reaching heat death. This is the most widely accepted scenario, but there is another possibility, one that is far more violent. What if dark energy is not constant? What if it is getting stronger? In the language of physics, dark energy is described by an equation of state parameter, usually denoted by the letter W. For a cosmological constant, W equals -1. This means dark energy has negative pressure, pushing space apart at a steady rate. But W could, in principle, have other values. If W is greater than -1, dark energy is weaker than a cosmological constant, and the expansion would slow down over time. If W is less than -1, dark energy is stronger, and the expansion would accelerate faster and faster. This latter case is called phantom dark energy, and it leads to a scenario known as the Big Rip. Here is how it would unfold. As the universe expands, phantom dark energy becomes more dominant. Its density increases, not decreases, with the expansion of space. This is counterintuitive. Normally, as space expands, matter and energy get diluted. But phantom dark energy does not dilute, it grows. And as it grows, it pushes galaxies apart faster and faster. Initially, the effects would be subtle. Galaxies would drift apart, and the expansion would accelerate, much as it does now. But over time, the acceleration would become extreme. Billions of years from now, galaxy clusters would be torn apart. The gravitational bonds holding them together would be overpowered by the expansion of space. Galaxies would find themselves alone, isolated in an ever-expanding void. Then, the expansion would begin to affect smaller structures. Individual galaxies would be ripped apart. Stars would be torn from their orbits and flung into the darkness. Our own Milky Way, held together by gravity for billions of years, would disintegrate. The sun would be torn from the galactic disk and left to drift through empty space. But the destruction would not stop there. As the expansion accelerates further, even solar systems would be torn apart. The gravitational bond between the Sun and Earth, strong enough to hold us in orbit for 4.6 billion years, would be overpowered. Earth would spiral away into the void, freezing as it went. And still, the expansion would continue. Months before the end, planets themselves would be ripped apart. The gravitational force holding the Earth together, the force that compresses rock and iron into a sphere, would be overcome by the expansion of space. The Earth would crack, crumble, and dissolve into fragments. In the final moments, atoms themselves would be torn apart. The electromagnetic force holding electrons in orbit around nuclei would be no match for the phantom dark energy. Electrons would be ripped away. Protons and neutrons, bound together by the strong nuclear force, would be pulled apart. Even atomic nuclei would disintegrate. And then, in the last instant, the fabric of space-time itself would be ripped apart. The universe would reach infinite expansion in finite time. Space, time, matter, energy, everything would be destroyed in a cataclysmic singularity. This is the Big Rip. How long do we have? If phantom dark energy exists, the timescale for the Big Rip depends on how much stronger than -1 the equation of state parameter is. Some models predict the Big Rip would occur in 20 billion years. Others suggest 50 billion years or more. But the key point is that it would occur. Unlike heat death, which happens asymptotically over infinite time, the Big Rip would be a finite endpoint, a moment when the universe ceases to exist. Is phantom dark energy real? We do not know. Current measurements of dark energy are consistent with a cosmological constant, but the uncertainties are large enough that phantom dark energy cannot be ruled out. The DESI observations suggesting that dark energy is evolving could, if confirmed, point toward phantom behavior. If the equation of state parameter is decreasing over time, moving from -1 toward more negative values, then we are on a path toward the Big Rip. But there is another, even more terrifying possibility. What if dark energy is not smooth and uniform, but varies from place to place? Some theories suggest that dark energy could be a field, like the Higgs field, that has different values in different regions of space. In one region, dark energy might be weak, causing slow expansion. In another, it might be strong, causing rapid expansion. And in some regions, it might be phantom, tearing apart everything in its path. If this is true, then the universe is not a uniform whole, but a patchwork of regions with different fates. Some parts might coast gently into heat death, others might collapse in a big crunch, and some might be ripped apart in a big rip. We would be living in a cosmic lottery with no way of knowing which fate awaits us. The Big Rip is not a mainstream prediction. Most cosmologists consider it unlikely, and current observations favor a cosmological constant. But it is not impossible. And the fact that our best theories allow for such a scenario is deeply unsettling. It reminds us that the universe is not guaranteed to be kind. The forces that govern the cosmos do not care about our survival. Dark energy, whatever it is, operates according to the laws of physics, not according to our preferences. If those laws lead to the Big Rip, then the Big Rip is what we will get. And unlike the heat death, which happens slowly over unimaginable timescales, the Big Rip would be catastrophic, sudden, and total. There would be no escape, no way to survive, no future civilizations, no distant descendants, no hope of preserving anything. In the final moments, as space itself tears apart, even the concept of future would cease to have meaning. The Big Rip is the ultimate apocalypse. Theory 9. We live in a simulation, and the evidence is mounting. Look around, the screen you are reading this on, the room you are in, the world outside your window. It all feels real, solid, tangible. You can touch it, measure it, interact with it. But what if none of it is real? What if you are living inside a simulation, a digital universe created by some advanced civilization, and everything you have ever experienced is just code running on a cosmic computer? This is the simulation hypothesis, and it has moved from science fiction to serious philosophical and scientific debate. The idea is simple. If it is possible to simulate a universe, even a simple one, then it is likely that advanced civilizations would create many such simulations. And if many simulated universes exist, then statistically, you are more likely to be living in a simulation than in the real universe. The logic is straightforward. There is only one base reality, but there could be countless simulations. The odds favor the simulation. This argument was famously articulated by philosopher Nick Bostrom in 2003. He proposed a trilemma. Either civilizations go extinct before they develop the technology to create realistic simulations, or they choose not to run such simulations, or we are almost certainly living in a simulation. If the first two options are false, the third must be true. For years, this was considered a philosophical curiosity, a thought experiment with no testable predictions. But recent developments in physics and computer science have made the simulation hypothesis more concrete. First, quantum mechanics. The behavior of particles at the quantum level is strange. Particles do not have definite properties until they are measured. Before measurement, they exist in a superposition of all possible states. This is not just a limitation of our knowledge. It is a fundamental feature of reality. The universe at the quantum level does not seem to have well-defined properties until someone looks. This is eerily similar to how a computer simulation might work. In a video game, the virtual world is not fully rendered until the player looks at it. To save computational resources, the simulation only computes what is necessary. Trees in the distance are not drawn in detail until you get close. Distant galaxies are not simulated in full unless you point your telescope at them. Quantum mechanics behaves the same way. The universe does not compute the exact position and momentum of a particle until you measure it. Until then, it exists in a probabilistic cloud of possibilities. This is exactly what you would expect if the universe were a simulation optimized to minimize computational cost. Second, the Planck length. In physics, there is a fundamental length scale called the Planck length, approximately 1.6 times 10 to the power of negative 35 meters. Below this scale, the concept of distance breaks down, and space itself becomes uncertain. Some physicists interpret this as evidence that space is not continuous but discrete, made of tiny indivisible units like pixels on a screen. If space is pixelated, then the universe has a resolution limit, just like a computer simulation. You cannot zoom in forever. At some point, you hit the smallest possible unit, and nothing exists below that. This is precisely what you would expect from a simulation running on a finite computer. Third, computational limits. In 2025, researchers at the University of British Columbia Okanagan used mathematical arguments based on Gödel's incompleteness theorems to show that the universe cannot be simulated by any computation. Their proof suggests that reality requires non-algorithmic understanding, something no computer can replicate. But this result, while intriguing, has been contested. Some argue that it only proves certain types of simulations are impossible, not all simulations. The debate continues. Fourth, glitches. If we live in a simulation, there should be occasional errors, bugs in the code, inconsistencies in the laws of physics. Some researchers have proposed looking for such glitches. For example, if space is discrete, then particles traveling at very high energies might interact differently than expected as they bump into the grid structure of space-time. Cosmic rays, the highest energy particles in the universe, could provide a test. So far, no definitive glitches have been found, but the search is ongoing. Fifth, the fine-tuning problem. The constants of nature, the strength of gravity, the charge of the electron, the mass of the Higgs boson, seem remarkably well tuned to allow life to exist. If any of these constants were slightly different, stars would not form, atoms would not bond, and life as we know it would be impossible. This fine-tuning has puzzled physicists for decades. One explanation is the multiverse. If there are countless universes with different physical constants, we naturally find ourselves in one where the constants allow life. But another explanation is that the constants were chosen deliberately by the simulation's creators. If the universe is a simulation, the fine-tuning is not a coincidence. It is a design decision. None of this proves we live in a simulation, but it makes the hypothesis harder to dismiss. And there is a darker implication. If we are in a simulation, then the simulators have power over us. They could pause the simulation, rewind it, or shut it down entirely. They could alter the laws of physics, insert new objects, or delete existing ones. We would have no way of knowing, no way of resisting, no way of escaping. Our entire existence would be at their whim. Furthermore, if we are in a simulation, there is no guarantee that the simulation will continue. Just as we turn off our computers when we are done with them, the simulators could turn off our universe. And when they do, everything would simply cease to exist. No warning, no transition, just oblivion. Some physicists argue that the simulation hypothesis is unfalsifiable and therefore not science. If the simulators are sufficiently advanced, they could hide all evidence of the simulation, making it indistinguishable from base reality. Others argue that the hypothesis is meaningless. If we cannot tell the difference between a simulation and reality, then the distinction does not matter. But there is one test that could, in principle, reveal the truth. If we develop the technology to create our own simulations, fully conscious beings living in a digital universe, then the simulation hypothesis becomes far more plausible. If we can create simulations, then it is likely that others have done so. And if others have done so, we are probably in one ourselves. This creates a recursive nightmare. We could be in a simulation, inside a simulation, inside a simulation, nested infinitely deep. Each layer would be unaware of the layers above, each believing itself to be the base reality. And at no point could we ever reach the real universe, because there might not be one. Reality itself might be simulations all the way down. The simulation hypothesis forces us to confront the fragility of our existence. If reality is code, then it can be rewritten. If the universe is software, it can crash. Everything we know, everything we are, could be nothing more than a temporary program running on a machine we will never see. And that, perhaps, is the most terrifying thought of all. Theory 10. Time itself could be running out. Time is the one constant we take for granted. Seconds tick by. Days turn into years. History flows from past to future in an unbroken stream. We measure it, depend on it, build our lives around it. But what if time is not fundamental? What if it is an emergent property, a useful illusion that arises from deeper laws? And what if that illusion is breaking down? This is not science fiction. This is a serious problem in quantum gravity, the attempt to unify Einstein's general relativity with quantum mechanics. And it suggests that time, as we understand it, might not exist at the most fundamental level of reality. In general relativity, time is part of space-time, a four-dimensional fabric that can bend and stretch under the influence of gravity. Time is not absolute. It flows at different rates depending on how fast you are moving and how strong the gravitational field is around you. This has been confirmed by countless experiments. Atomic clocks on satellites tick faster than clocks on Earth. Time slows down near a black hole. Time, in relativity, is flexible. But in quantum mechanics, time is different. It is a fixed background parameter, a stage on which quantum events unfold. Particles exist in superpositions, probabilities evolve, and measurements collapse wave functions, all within a framework where time marches forward uniformly. These two views of time are incompatible, and when physicists try to combine them into a theory of quantum gravity, something strange happens. Time disappears. One of the most famous equations in quantum gravity is the Wheeler-DeWitt equation, derived in the 1960s. It describes the quantum state of the entire universe, but the equation has no time variable. There is no parameter that tracks the evolution of the universe from past to future. The equation is timeless. According to Wheeler-DeWitt, the universe does not change. It simply is. This is called the problem of time in quantum gravity, and it has baffled physicists for decades. How can we reconcile our everyday experience of time's flow with a fundamental theory that says time does not exist? One proposed solution is that time is emergent. Just as temperature emerges from the motion of individual atoms, time might emerge from the interactions of quantum fields or the entanglement of quantum states. At the deepest level, there is no time, just a vast web of quantum correlations. But at our level, in our macroscopic world, those correlations give rise to the sensation of time's passage. If this is true, then time is not fundamental. It is a byproduct, an approximation that works well in the classical world, but breaks down at the quantum level. And if time is emergent, it could, in principle, cease to emerge. Imagine if the quantum correlations that give rise to time became disordered. Imagine if the entanglement structure of the universe broke down, or if the fundamental laws changed in a way that prevented time from emerging. What would happen? We do not know, but the implications are unsettling. If time is not fundamental, then the past and future are not as distinct as they seem. The entire history of the universe, from the Big Bang to the present, might be encoded in a single, timeless quantum state, and our perception of moving from past to future might be an illusion, a trick of our macroscopic perspective. Some physicists take this idea seriously. Julian Barbour, a British physicist, has argued for decades that time does not exist. In his view, the universe consists of a vast collection of possible configurations, which he calls nows. Each now is a complete snapshot of the universe at a given instant. Our perception of time arises because our memories link these nows together, creating the illusion of flow. But fundamentally, there is no flow. There is only a landscape of nows, existing simultaneously, with no past or future. If Barbour is right, then the future is not ahead of us, and the past is not behind us. They are all here now, in different parts of the timeless quantum state. We experience them sequentially because of the way our brains process information, but the sequence is not real. It is a mental construct. This view has profound implications. If time is an illusion, then change is an illusion. Nothing truly happens. It only seems to happen from our limited perspective. The universe is static, frozen, unchanging, a four-dimensional crystal in which every moment exists eternally. But there is another, more disturbing possibility. What if time is real at our level but fragile? What if the conditions that allow time to emerge are temporary and could change? Some cosmologists have speculated that in the very early universe, before inflation, time might not have existed in the way it does now. The quantum state of the universe might have been so chaotic, so disordered, that no consistent arrow of time could emerge. Only after inflation smoothed out the fluctuations did time begin to flow in a coherent way. If that is true, then time had a beginning. And if it had a beginning, it could have an end. Imagine a future in which the expansion of the universe, driven by dark energy, continues to accelerate. Eventually, galaxies drift apart, and the cosmic horizon shrinks. Future observers would find themselves in an increasingly empty, isolated cosmos. The entropy of the universe would approach its maximum, and the conditions that allow time to emerge would break down. In such a future, time might stop making sense. Clocks would tick, but there would be no events to measure, no processes to mark the passage of time. The universe would enter a state of stasis, where nothing changes, and the concept of time becomes meaningless. This is not the heat death, where energy is evenly distributed and no work can be done. This is something deeper, the end of time itself. The arrow of time, which points from past to future, would dissolve. And without time, there is no change, no causality, no sequence of events. The universe would become a frozen tableau, a timeless void in which nothing happens. Could we survive such a transition? Almost certainly not. Our brains, our bodies, our very thoughts depend on the flow of time. Without time, there is no metabolism, no neural activity, no consciousness. We would not experience the end of time. We would simply cease to exist as dynamic beings. The end of time is not a prediction. It is a possibility, a speculative consequence of taking quantum gravity seriously. But it reminds us that time, like space, like matter, like energy, is not guaranteed. It is a feature of our current universe, shaped by the laws of physics we observe. And if those laws change, time could change too, or it could vanish entirely. You came here to confront 10 theories that terrify scientists. You have walked through universes that collapse in an instant, black holes that wander unseen, and a cosmos that might be nothing more than a digital illusion. You have faced the possibility that your memories are false, that dark energy is changing, that time itself could end. These are not certainties. They are not even predictions. They are possibilities, edges of our knowledge, places where the math leads us into dark and unfamiliar territory. Science does not deal in absolute truths. It deals in models, approximations, probabilities. And when we push those models to their limits, we find scenarios that unsettle us. But that is the point. Science is not meant to comfort us. It is meant to reveal reality, no matter how strange or unsettling that reality turns out to be. The universe does not owe us stability, predictability, or safety. It operates according to laws we are only beginning to understand, and those laws permit outcomes we would rather not imagine. The false vacuum could collapse tomorrow, or it could remain stable for a Google years. Rogue black holes could be drifting through our galaxy right now, invisible and hungry, or they could be rare enough that we never encounter one. Dark energy could be constant, or it could be evolving toward a big rip. We could be living in base reality, or we could be characters in a simulation, unaware that our entire universe is code running on a machine we will never see. We do not know, and that is the most honest answer science can give. But uncertainty is not the same as ignorance. Over the past century, we have learned an astonishing amount about the cosmos. We know the age of the universe to within a few million years. We know what it is made of, how it began, how it has evolved. We have mapped the cosmic microwave background, detected gravitational waves, photographed black holes, and measured the expansion of space itself. These are extraordinary achievements, monuments to human curiosity and ingenuity. Yet every answer raises new questions. Every discovery reveals new mysteries. And the deeper we look, the stranger the universe becomes. The theories you have encountered today are not final. They are works in progress, hypotheses to be tested, puzzles to be solved. Some will be confirmed by future observations. Some will be refined or abandoned. And some will lead us to entirely new ideas, concepts we have not yet imagined. That is how science works. It is a process, not a destination. And the journey, for all its uncertainties and unsettling revelations, is what makes it worth pursuing. So what should we do with this knowledge? How should we live, knowing that the universe is stranger and more fragile than we thought? We should not despair. The false vacuum has not decayed. The Big Rip has not begun. Rogue black holes, if they exist, have not found us. We are here now, alive in a universe that, for all its mysteries, is magnificent. The same physics that permits vacuum decay also allows stars to shine. The same quantum mechanics that suggests we might be Boltzmann brains also enables the complexity and beauty of life. The universe is not just a collection of threats, it is a cosmos of wonder. We should keep searching. Every telescope we build, every experiment we run, every equation we solve brings us closer to understanding. The Hubble tension may reveal new physics. The DESI observations may unveil the nature of dark energy. The search for rogue black holes may uncover hidden populations of cosmic wanderers. And the quest for a theory of quantum gravity may finally tell us whether time is fundamental or emergent. We should embrace the mystery. Not knowing is not a weakness. It is an opportunity. The universe is vast, and we have only just begun to explore it. The questions that terrify us today might inspire the breakthroughs of tomorrow, and the theories that seem impossible now might become the foundations of future science. But above all, we should remember this. The universe does not reveal its secrets easily. It hides them in the quantum foam, in the warping of space-time, in the depths of black holes, and the vast emptiness between galaxies. It challenges us to look harder, think deeper, and question our assumptions. And every time we do, we find something unexpected. That is the nature of the cosmos. It is strange, it is terrifying, and it is beautiful beyond measure. The 10 theories you have explored are reminders that reality is not what it seems. They are invitations to wonder, to question, to push the boundaries of knowledge. And they are warnings that the universe, for all its elegance and order, is not bound by our expectations. So look up tonight. Look at the stars, the galaxies, the cosmic web stretching across billions of light years. Know that somewhere out there, processes are unfolding that we can barely imagine. Black holes are wandering. Dark energy is expanding space. The false vacuum is holding, for now. And the universe, indifferent to our fears and our hopes, continues its inexorable journey through time, or perhaps through timelessness. We are passengers on this journey, witnesses to a story that began long before us and will continue long after we are gone. We are made of stardust, shaped by the same forces that govern galaxies and black holes, bound by the same laws that might one day tear everything apart. And in that, there is a strange kind of comfort. We are not separate from the universe. We are part of it. Our atoms were forged in dying stars. Our existence depends on the delicate balance of forces that hold matter together. When we study the cosmos, we are studying ourselves. The theories that terrify us are not enemies. They are mirrors, reflecting the universe back at us in all its complexity and mystery. And if we are brave enough to look, to truly look, we might just find something extraordinary. Because the most terrifying possibility of all is not that the universe is strange or fragile or indifferent. It is that we might never find out what lies beyond the edge of what we know. And that would be the greatest tragedy of all.